If you used an early smartphone, you remember the autocomplete feature, that little bar above the keyboard guessing your next word. Today, we have AI passing the bar exam and writing complex software. However, beneath the hood, that old autocomplete and today's high-performing AI operate on the same base technology. This process is called autoregressive decoding. You start with a text stem, like to be or not to. The model predicts a single word next, be. Then it takes that entire new phrase, loops it back in, and predicts the next word. In many ways, machine learning is just fancy counting. We can trace this back to the 1980s with Bayesian language models. If you feed one of these models the phrase, it was the, it looks back at its training data to count what words followed that exact sequence. It builds a probability dictionary. It might calculate a 33% chance the next word is H and a 16% chance it's worst. The model then randomly samples from this list to pick the next word. There is no consciousness or deep comprehension happening here. The system isn't thinking about the meaning of the words. It is a statistical engine, blindly predicting exactly one token at a time based on past patterns. But early text predictors hit a wall quickly. They had a tiny context window, meaning they could only remember a few words at a time. Without enough memory to know when a sentence should end, they got stuck in repetitive probability loops, spitting out the same phrase over and over. Because they couldn't reason, they acted like fuzzy lookups into their training data. If you asked an early Google chatbot for a restaurant recommendation, it might randomly reply with, "TripAdvisor staff removed this post." It didn't know what the words meant, it just knew that specific string of text appeared frequently next to restaurant reviews online. Left on its own, a raw prediction engine is chaotic. To make this simple autocomplete useful, engineers had to scale it up to an unimaginable size and build new ways to steer it. This chart shows the growth of parameters in language models. Think of a parameter as a single connection in the network, similar to a synapse in a biological brain. In 2018, models like BERT had around 340 million parameters. Today, models are running on trillions of parameters. At the same time, the context window expanded massively. A 1980s model could hold maybe 4 words in memory before making a prediction. Today's models can hold up to 2 million tokens at once, giving them access to an enormous amount of information before they generate a single word. At this scale, the models began to demonstrate capabilities that weren't in the training data, a phenomenon called emergent behavior. Give these trillions of parameters instructions for a logic puzzle without any examples, and they can generalize to find a solution. This exponential increase in scale changed the nature of the counting machine, evolving it from a text predictor into a flexible problem-solving tool. But how do you control a system with a trillion different pathways? You steer it. That's where prompt engineering comes in. You use specific language cues to navigate the model's massive probability space. Take role prompting. If you ask a language model a complex math question, it might pull from millions of incorrect answers scattered across internet forums. But if you start your prompt with, "You are an MIT mathematician," you shift the model's probability distribution. You force it to draw from a subset of data populated by people who actually know how to do the math. Then there is chain of thought prompting. If you ask a model to think step by step, it writes out its logic before giving a final answer. By forcing the model to generate a longer sequence of text, you give the network more computational surface area to catch a mistake before it outputs the final number. Prompting functions as a high-precision steering mechanism, forcing the model into a specific, accurate quadrant of its statistical memory. Engineers can also steer the model by tweaking the network itself. A technique called LoRa, or low-rank adaptation, lets developers project a small set of auxiliary weights onto a base model. Instead of retraining the whole system, they can sideload these smaller modules to give the AI a specialized flavor, like making it speak strictly in Shakespearean sonnets. To make these models genuinely helpful, companies rely on RLHF, reinforcement learning with human feedback. They collect thousands of human ratings on the model's outputs to teach it what people actually prefer, prioritizing helpfulness over pure internet regurgitation. By adjusting these underlying network weights, engineers transform a chaotic web scraper into an aligned and helpful digital assistant. Despite this advanced steering, these are still statistical prediction engines, and they fail.
they hallucinate fake information with extreme confidence. In one legal case, a lawyer used an AI to write a brief, and the model completely invented legal precedents, citing a Vargas decision that simply never happened. Language models do not inherently understand the physical or logical rules of the real world. For example, when researchers had a language model play a game of chess, it initially played well, but eventually its queen just jumped straight over a knight to capture a piece. It doesn't comprehend the spatial limits of the board. Because of this, developers have to build external guardrails. They add policy layers that intercept and block illegal or unsafe outputs before they reach the user. They also use RAG, or Retrieval Augmented Generation. Instead of letting the AI guess the facts, RAG connects the model to a verified external database, forcing it to retrieve accurate data before it starts generating text. An AI remains a stochastic engine. It relies on probability, meaning it cannot operate safely in a high-stakes environment without a strict human-designed safety architecture wrapped around it. The focus is now shifting from models that simply generate text to agentic workflows, systems where AI uses planning and external tools to impact the world. In the React framework, the model is prompted to cycle through a specific loop. It reasons about a complex problem, takes a concrete action to test a hypothesis, like searching for a specific film's release date, observes the result, and adjusts its plan to solve the puzzle. With techniques like Toolformer, the AI learns to pause its own text generation when it hits a gap in its knowledge. It writes a command to an external API, like running a calculator, and then injects that factual result right back into its response. By integrating reasoning loops and external APIs, the predictive engine transitions from a passive text generator into an active component capable of executing multi-step tasks. If you want to move beyond the theory and actually start building with these models yourself, check out the Learn by Doing with Stephen YouTube channel. You can also listen to deep dives on the Stephen Data Talk podcast, available on YouTube Music and Spotify. Understanding how prediction actually works allows you to use these tools effectively as they become integrated into every layer of our digital lives. In 1989, deep learning was defined by the universal approximation theorem. It states a single hidden layer neural network can approximate any continuous function. The model recalculates its internal weights to thread the needle, mapping any input to any continuous output without error. However, while these networks possess the mathematical capacity to perfectly map any function, they often fail when transitioning from a controlled dataset to the noise of the real world. This occurs because the raw computational power required to fit any curve also enables a network to memorize its training data. This creates a system that is mathematically precise during training, but structurally fragile during deployment. Modern generative architectures employ structural workarounds to these foundational flaws, moving beyond the limitations of single-shot function approximation. The theoretical capability to learn any mapping is tied to the risk of memorizing noise over signal. Addressing this required changing how we structure deep learning tasks. Researchers took a standard image dataset and completely randomized the labels. A cat labeled a truck, a dog a plane. Despite having no semantic meaning, the network achieved near 100% accuracy on this training set, while test accuracy flatlined. The model did not recognize visual features or semantic concepts. It operated as a function approximator, finding a maximum likelihood estimate, memorizing the random noise to reduce its error to zero. This creates a rigid internal representation. When the network encounters out-of-distribution, or OOD data, inputs falling outside the precise coordinates of its memorized training set, the mapping breaks down. We see this in simple tasks, like training a network to colorize photos. Models will color the closed mouths of dogs pink because they over-indexed on training images where dogs had their tongues out. In high-stakes environments, OOD data leads to fatal errors. An autonomous vehicle recently swerved into a concrete barrier because that specific barrier was not present in the original training data. The model encountered a novel object and failed to resolve it. In these OOD scenarios, standard deep neural networks lack the architecture to calculate or express their own uncertainty. Standard deep learning maps inputs to outputs without a mechanism for self-correction. A model that memorizes its training data remains blind to the gaps in its own knowledge. Mathematical rigidity exposes adversarial vulnerability. Normally, we lock input data and shift internal weights to minimize loss. Adversarial attacks invert this, freezing weights and unlocking the input. A microscopic perturbation maximizes the network's error. By perturbing the input along the gradient, we force the network to assign an incorrect classification while maintaining maximum statistical confidence in that error. These vulnerabilities extend to the physical world. Researchers used a 3D printed turtle with a mathematically engineered surface pattern to trick computer vision models into classifying it as a rifle. Adversarial fragility is a mathematical consequence of relying on single-shot function mapping to process complex data. To bypass the memorization trap, modern generative architectures move away from single-shot generation. This shift is evident when comparing older frameworks like VAEs and GANs against diffusion models.
Older models attempted to map from a compressed latent space directly to a final image in one pass. This was often unstable, frequently resulting in mode collapse, where the network produced only average, repetitive outputs. Diffusion models replace that mechanism with a sequence of careful iterative steps, beginning with what we call a forward process. We take a source image and incrementally add layers of random Gaussian noise until the image is pure static. This forward process is a simple mathematical decay that requires no training. The neural network handles the reverse process. Given a noisy image at step t, it predicts the residual noise difference from t-1. We optimize this using a mean squared error loss function, comparing the predicted noise against the actual noise added. Once trained, we feed pure random noise into this reverse loop. The network iteratively subtracts noise step by step, allowing it to produce diverse, high-fidelity generations. By asking the network to perform a repeatable, narrow task over multiple steps, diffusion avoids the fragility associated with single-shot function approximation. This iterative framework also applies to natural language processing. A large language model first performs tokenization. Raw text breaks into discrete blocks, encoded into numerical sequence IDs. The objective is autoregressive next token prediction. Given a sequence of tokens, it outputs a probability distribution for the next token. Because the training data consists of vast amounts of existing text, the data provides its own labels. This allows for massive, self-supervised training without manual annotation. The network's weights are optimized by calculating the cross-entropy loss between its predicted probabilities and the actual token found in the training document. As these models scale in parameter count and training data, we see step changes in their ability to handle complex tasks. The same next token prediction loop begins to generate coherent code, structure complex logic, and perform cross-lingual translation. These capabilities suggest that while the underlying objective is simple, the sheer scale of the prediction loop allows the model to capture deep patterns within human language. We can now connect the OOD data boundaries, the denoising timelines of diffusion, and the autoregressive sequences of language models back to the universal approximation theorem. The current frontier circumvents the vulnerability of single-shot memorization by adopting stepwise iterative optimization across both vision and language tasks. Even with these improvements, deploying these models in real-world scenarios still carries risks. Several frontiers remain unsolved. The field is still working to mitigate hallucinations, calculate explicit model confidence, and enable long-term logic planning. You can experiment with these concepts and build these architectures yourself on the Learn by Doing with Stephen YouTube channel. For ongoing discussions on the theoretical boundaries of machine learning, subscribe to the Stephen Data Talk podcast on Spotify and YouTube Music. Machine learning is no longer limited by the basic math of approximation, but by our ability to refine the sequences that guide its outputs. Traditional deep learning models are trapped inside a static digital sandbox. They can process millions of labeled photographs and reliably identify an apple. But if you drop that same AI into a physical, moving space, it has absolutely no idea how to interact with that object.
To solve problems in the physical world, an AI needs to move past passive observation. It has to act, make mistakes, and learn from its surroundings. This process is called deep reinforcement learning. An agent acts in an environment. This action updates the state, returning a reward. But like choosing $5 today over 10 years from now, it applies a discount factor, forcing the algorithm to prioritize immediate successes over distant payoffs. The ultimate goal of this loop is to maximize total lifetime success. And figuring out the mathematics to achieve that goal led researchers to develop two completely different philosophies of machine learning. The first philosophy is called value learning. To test it, researchers used the heavily structured environments of vintage video games. They built something called a queue function. The queue function looks at the exact current state of the game and assigns a strict numerical value to a fixed menu of possible actions, moving left, moving right, or staying still. It calculates which single button pressed yields the highest expected point total. By rigorously predicting the point value of every choice, the algorithm occasionally discovers entirely counterintuitive strategies. In Breakout, the queue function realizes that the highest future reward actually comes from moving away from the ball, allowing it to slip into a corner and ricochet behind the blocks to rack up massive points. However, this method has a strict mathematical limitation. It is completely deterministic. It only functions when you have a discrete, highly limited menu of choices to evaluate. Calculating the exact point value of 3 arcade buttons works brilliantly on a screen. But navigating the messy, physical reality of our world requires a system that can handle an infinite number of highly nuanced decisions. When you drive a car, you aren't choosing between 3 buttons. You are constantly making micro-adjustments to the steering wheel across an infinite range of angles. This is known as a continuous action space. To solve for this, engineers use policy networks. Instead of predicting the exact value of an action, the network predicts a probability distribution, typically a Gaussian curve. The network outputs 2 numbers, a mean, which is its best guess for the optimal steering angle, and variance, which provides a mathematical margin to explore slightly different angles. The agent samples an angle from this curve and executes the turn. When the car invariably veers off the road, the algorithm runs a backpropagation sequence. It mathematically decreases the probability of the exact actions that led to the crash and increases the probability of the actions that kept the vehicle centered. This creates a major physical problem. In the real world, you cannot run an autonomous vehicle into a wall 10,000 times to collect failure data. The cost of reaching termination is too high. To bridge this gap, robotics labs at institutions like MIT build hyper-realistic physics simulators. The AI plays out its thousands of disastrous mistakes entirely inside a digital twin of our world. By directly shaping the probability of success inside this safe, simulated crucible, the system eventually learns to navigate continuous physical environments perfectly before it is ever installed into a piece of physical hardware. To see exactly what deep reinforcement learning is capable of, researchers applied it to Go, a strategy game containing more legal board positions than there are atoms in the observable universe.
Google DeepMind conquered the game by fusing both learning philosophies together. First, a policy network looks at the board and drastically prunes the near-infinite search space down to a handful of high-probability optimal moves. Then, the second half of the brain, the value network, takes over. It immediately calculates an aggregate win percentage for those few remaining paths, eliminating the need to simulate the game all the way to the final move. This solved a massive problem in strategy games. In matches like chess or Go, the reward signal is incredibly sparse. A player might make a brilliant structural move in hour 1, but they won't receive the actual reward of winning the game until hour 4. DeepMind's value network provided instant mathematical feedback for every individual step. Eventually, the engineers stopped showing the algorithm human gameplay data entirely. The agent started with a blank slate, playing millions of matches against itself, learning exclusively from the sparse rewards of its own digital victories and defeats. It developed strategies that grandmasters had never documented. This marked the point where the models stopped mimicking historical human behavior and used interaction and exploration to surpass human logic on their own. Understanding the math behind value networks and policy gradients is one thing, but actually building these architectures yourself is the logical next step.
If you're ready to get your hands dirty, head over to the Learn by Doing with Steven YouTube channel. You'll find practical, step-by-step tutorials to start writing the code that powers these AI environments. And if you want to explore the data models that make these algorithms possible, check out the Steven Data Talk podcast, available on Spotify and YouTube Music. All the links you need to start building are down in the description. Thanks for watching.
The most valuable data we have doesn't sit still, it flows. It's a continuous sequence of events where the order of the information matters just as much as the data itself. In global finance, predicting the next market movement is impossible without tracking the exact timeline of the millions of trades that preceded it. In medicine, the rhythm of a heartbeat recorded on an EKG is a sequence where a single disruption tells a critical diagnostic story. For years, the foundational tool was the feed-forward neural network. Data goes into input nodes, weight supply, and a prediction emerges. But these models process every input in total isolation. They evaluate sequential data points individually, completely blind to their arriving order. It's like trying to predict exactly where a moving ball will bounce next by looking at a single static photograph of it in midair. Without seeing its past trajectory, any guess is just random chance. To process sequential data, deep learning engineers had to find a way to force the concept of time into neural networks. But as the sequences grew longer, they would eventually realize that to build true artificial memory, they had to abandon the timeline altogether. The ultimate test of sequence modeling is human language. But before a neural network can track the order of words in a sentence, we have to solve a simpler problem. Machines cannot read text. They only process numerical inputs. The earliest approach to this was one-hot encoding. You create a massive dictionary of every known word and assign each word to a specific slot in an array of zeros, marked by a single one. With a vocabulary of tens of thousands of words, you end up with massive, mostly empty vectors floating in space. It is computationally wasteful, and it tells the network absolutely nothing about what the words actually mean. The modern solution to this problem is called an embedding. Instead of tracking a giant binary grid, an embedding condenses that vast vocabulary down into a dense, continuous vector of numbers, mapped out in a multi-dimensional coordinate space. By mapping words this way, semantic meaning translates directly into geometric proximity. Concepts that are related, like deep and learning, naturally cluster close together in the mathematical space. We successfully converted abstract language into spatial geometry. But the network still needed a mechanism to read these geometric points sequentially, exactly as they appear in a sentence. How do you give a memory to a feed-forward network that is strictly designed to reset after every single input? The engineering solution was the Recurrent Neural Network, or RNN. It introduced a feature that standard models lacked, a continuous feedback loop. An RNN maintains a dynamic variable called a hidden state. After the node processes an input, it loops its output back into itself. If you unroll this loop over time, it becomes a horizontal timeline of identical nodes connected by a linear path. At any given time step t, the output is calculated using both the new input arriving right now and the hidden state passed forward from the previous step, t-1. The network isn't learning a new set of rules for every step. It reuses the exact same weight matrix, updating it sequentially at every point along the timeline. The RNN successfully forces chronological order onto the data, but that rigid step-by-step dependency introduces a mathematical bottleneck that eventually breaks the entire system. For a neural network to learn, it has to calculate its errors and adjust its weights. In an RNN, it has to do this in reverse, tracing the error signal backward through the timeline. This process is called backpropagation through time. Because the sequence is linked step by step, backpropagation requires chaining matrix multiplications together, using that exact same set of weights repeatedly for every single time step. If those weight values are even slightly less than 1, repeatedly multiplying them against each other causes the error signal to shrink exponentially as it moves backward. This exponential decay is known as the vanishing gradient problem. In practice, this means the error signal fades to 0 before it can reach the earliest nodes in the sequence. The network literally forgets the context of the data it saw at the beginning of the run.
Engineers built variations like LSTMs that use internal gates to selectively hold on to information longer, acting as temporary band-aids. But they could not bypass the underlying bottleneck of sequential processing. Processing data strictly chronologically guarantees computational decay over long distances. To handle massive sequences effectively, deep learning required a different structural logic. The challenge was clear. How do you analyze a strict sequence without getting trapped by a step-by-step timeline? The solution was an architecture that completely abandons recurrence. It's called self-attention. Instead of reading data one step at a time, self-attention pulls in the entire sequence and looks at every piece of data simultaneously, in parallel. To ensure the network still knows the order of the inputs without a timeline, a mathematical marker called positional encoding is injected directly into the data before processing begins. To figure out what matters most in that sequence, the network acts like a search engine. When you search a massive video library, you input a query and the system compares it against the keys, the titles of every video, to find the closest match. Self-attention does this mathematically by splitting the sequence data into 3 distinct parallel matrices: the query, the key, and the value. By formatting the data as a set of simultaneous search queries, the architecture trades the rigid limitations of linear time for the absolute precision of mathematical relevance. The query matrix represents the specific item the network is currently analyzing in the sequence. The key matrix holds the characteristics of every other available item in that exact same sequence. The network calculates relevance by taking the dot product, or cosine similarity, between the query and the keys. This generates a raw mathematical score, indicating exactly how closely related those items are in the coordinate space. Those raw scores are run through a softmax function, which squashes them into normalized percentages between 0 and 1. This mask is multiplied by the value matrix, illuminating highly relevant features and dimming irrelevant noise. Because this extraction happens in parallel, it entirely circumvents the vanishing gradient problem. The network can draw a direct, immediate connection between any 2 points, regardless of how far apart they are in the sequence. That entire operation, the query, key, and value calculation, represents just a single attention head. With multi-head attention, you clone this process, stacking the operations vertically. One head might evaluate syntax, another tracks semantic meaning, and another monitors long-term context, all in parallel, locking together to form the transformer architecture. This massively parallel attention architecture is the core engine running modern large language models and generative AI, and it extends far beyond text. Vision transformers now use this exact same self-attention mechanism to process complex imagery without relying on recurrence. In biology, attention models decode the complex sequences of life itself, using sequence data to accurately predict 3-dimensional protein structures. Understanding these abstract mathematical architectures requires bridging the gap between theory and hands-on coding. To build these concepts yourself, subscribe to the Learn by Doing with Stephen YouTube channel for applied tutorials. And to explore deeper discussions on data architecture, listen to the Stephen Data Talk podcast, available now on YouTube Music and Spotify. Take a close look at these 3 people. Examine the texture of the hair, the fall of the light, and the way the skin creases. Which one of them is actually real? None of them. Every face on your screen was synthesized from scratch by an artificial intelligence. In traditional supervised learning, an AI acts as a digital cataloger. We provide millions of images labeled by humans, and the machine learns to recognize the specific patterns that define a category, like a face or a car. Modern unsupervised learning models operate differently. Instead of relying on human labels, these systems are designed to identify the internal rules and patterns of raw data on their own. By modeling a dataset's underlying probability distribution, these systems can move beyond recognition to generate entirely novel samples. They learn the mathematical likelihood of where a pixel should be, allowing them to invent data that follows the same rules as the real world. To bridge the gap between identifying an object and creating one, computer scientists developed 2 distinct architectures, each operating on a different mathematical philosophy. The first path relies on latent variables. These are the invisible parameters that define a dataset, the specific tilt of a head, the shade of a skin tone, or the exact hair color. A classic autoencoder finds these variables by forcing an image through a mathematical bottleneck. It compresses the data into a dense vector of representative features. Then a second network tries to reconstruct the original image from that tiny fingerprint. However, a standard autoencoder is deterministic. Because it maps inputs to fixed points, it can only reproduce what it has already seen. It memorizes existing data, never creating anything new. The variational autoencoder, or VAE, solves this by turning that bottleneck into a probability distribution. Instead of a single point, the model learns a range of likely values.
This creates a continuous latent space where every point represents a valid output. Because the space is smooth and has no gaps, the AI can sample any random coordinate to generate a brand new, coherent image. This provides a specific interface for generation. By isolating one variable, like head pose, we can adjust it while the rest of the image, like identity or background, remains unchanged. VAEs act as a structured control board for reality. They give researchers the ability to manually tune the underlying variables that govern a synthetic generation. But there is another way to generate data. What if we stop trying to organize the variables and focus entirely on creating results indistinguishable from the real thing? This is the logic of the Generative Adversarial Network, or GAN. It is a system built on a zero-sum competition between two different neural networks. The generator is the first network. It transforms random noise into a synthetic imitation of the training data. The discriminator is the detective, comparing this work against authentic examples. If it detects a discrepancy, it flags the forgery, forcing a retry. This creates an arms race. Each time the discriminator patches a fake, the generator learns to improve its output. This continues until the forged data is so accurate that the discriminator can no longer tell the difference between synthetic and real. This adversarial approach has evolved into tools like CycleGANs. By linking systems together, researchers can translate styles across domains, like converting a video of a horse into a zebra while maintaining the original movement. Researchers also use this method for high-fidelity voice cloning. By analyzing audio spectrograms, a GAN learns the unique frequency and cadence of a specific speaker, allowing it to synthesize speech that matches the target's voice. GANs produce these results not through a careful understanding of features, but by optimizing a generator to successfully defeat a dedicated discriminator. Whether an AI is compressing data or training through competition, it is ultimately mapping the statistical distribution of the world around us. Once a model understands these distributions, it can simulate reality. Autonomous systems use this logic to generate rare, dangerous outliers, like a pedestrian suddenly appearing from behind a car, to train their software before it ever reaches the road. These generative foundations are currently driving breakthroughs in drug discovery, adaptive robotics, and digital media. We have moved past teaching machines how to look at our world and have finally given them the tools to dream up their own. If you want to dive deeper into the neural networks and the mathematics of the modern AI landscape, join our community. Follow Learn by Doing with Steven, Sunang Shengzhi, as well as Steven Data Talk and Steven Shujun Nantan on Xiaohongshu, our official WeChat account, YouTube, and Spotify. Check the show notes for the Linktree URL at linktree.ee/learnbydoingwithsteven to subscribe and continue your learning journey. Take a look at this crowded New York City block. In a fraction of a second, your brain processes the overlap of the vehicles, identifies the pedestrians in the crosswalk, and predicts exactly where they are going to step next. But a computer sees none of that. To a machine, this rich, dynamic environment is a massive grid of raw RGB pixel intensities, entirely composed of numbers arranged in rows and columns. If you feed this image into a traditional neural network, the system requires you to flatten that grid. Every row of pixels is stacked end-to-end into one extremely long, single-file line of data. By forcing a two-dimensional image into a one-dimensional line, the network loses track of which pixels were originally next to each other. The shape of a car door or the curve of a traffic light is erased before the computer even begins to process it. To give a machine the ability to actually see, we have to respect the two-dimensional structure of the data.
We need a mathematical operation that scans the image in small, overlapping patches, rather than trying to process a single string of numbers. Machine sight relies on capturing and maintaining the spatial relationships between pixels, rather than simply counting them individually. This local scanning method is called a convolution. The network uses a small numerical matrix called a filter. It slides sequentially across the main grid, performing element-wise multiplication. If the underlying pixels align with the math, say forming a diagonal line, the output spikes, lighting up a neuron to record a match. For decades, human engineers had to write code to create these filters manually. They had to guess the exact math required to detect an edge, a shadow, or a corner. Curious, engaged tone. Modern convolutional neural networks skip that human bottleneck entirely. They ingest millions of data points, calculate precise mathematical patterns, and identify human eyes or wheels. Computer vision efficiency improved as we moved away from human-designed filters, allowing the data itself to define the mathematical requirements for detection. But knowing where the edges are isn't enough to recognize a complex scene. A single layer of detection only gives the network a scattering of lines. To build comprehension, the network must zoom out. It does this through an operation called max pooling. By scanning the data and keeping only the highest values, the network shrinks the dimensions of the grid. This condenses the information, so the next layer of filters can analyze a much wider receptive field. By stacking these steps, the network builds hierarchical abstraction. The first layer finds basic lines. The second layer pools them into geometric shapes. The third layer synthesizes those shapes into complete structures, like the profile of a human face. Through repeated convolutions and pooling, the network bridges the gap between raw data and usable concepts. It organizes thousands of microscopic pixel gradients into high-level, recognizable structures. Everything we just covered makes up the first half of a convolutional neural network. It is a feature extraction factory that can be plugged into vastly different end goals. In a basic classification task, the model uses extracted features to predict a single label for the entire image. The output here is simply taxi. Object detection demands much more. The network must label the object, but also predict its exact coordinates, drawing a bounding box to isolate it from the background. Take a look at this scene. Semantic segmentation pushes the network even further. Instead of an overarching label, the network must classify every single pixel independently, drawing precise boundaries between the animal, the tree, and the sky. Inside this autonomous vehicle, the network isn't classifying categories at all. Combining live visual data with digital maps, it utilizes continuous regression to output a numerical value dictating the exact angle of the steering wheel. Processing data spatially through local patches is an elegant mathematical concept. That single principle scales to solve nearly every complex visual task we give machines today. By evaluating images geometrically, these networks assist medical professionals identifying micropatterns in digital mammograms and provide the spatial awareness required for advanced robotics. Follow our channels to master the architecture behind artificial intelligence. Use the link tree below to connect on Xiaohongshu, WeChat, YouTube, and Spotify. Subscribe, share this with anyone building in AI, and keep learning.
This chart shows how AI systems historically responded to receiving more data. On the bottom axis, we have the sheer amount of data fed to a system, and on the vertical axis, its accuracy. If you test older, traditional machine learning models, like decision trees or logistic regression, they hit a hard ceiling. Even after absorbing thousands of hours of data, their accuracy flattens out into a plateau. They simply didn't know what to do with all that extra information. But an entirely different architecture called a deep learning network acts differently. If you map a neural network on this same graph, that plateau disappears. Instead of flattening out, a deep learning model continuously digests that massive ocean of data, and its accuracy climbs steadily upward. The hardware capable of processing that kind of scale didn't originate in massive corporate data centers. About 15 years ago, an undergrad named Ian Goodfellow built a controversial computer server directly inside his Stanford dorm room. By using consumer-grade GPUs, hardware originally meant for video games, to train neural networks, he proved these massive computations could be executed efficiently.
Combining immense data with heavy GPU computing unlocked a predictable mathematical reality known as scaling laws. Researchers realized that if they purchased a specific number of GPUs and added a specific volume of data, they could precisely forecast how well the resulting AI would perform. That predictability allowed companies to invest billions with total confidence. Artificial intelligence shifted from a volatile academic experiment into a highly reliable industrial-scale engine. To navigate this ecosystem, you have to look at the modern AI stack. The base layer begins beneath AI entirely. It starts with core computer science fundamentals, understanding how memory, software architecture, and code physically interact with the machine. Stacked directly on top of that is traditional machine learning. These are the classic algorithms built to extract basic patterns from data without relying on massive layered networks. The critical middle layer is the deep learning layer. This is the highly scalable neural network engine that digests the world's raw data and drives the heavy computations. Sitting at the very top is generative AI. This is the consumer-facing application layer that writes code and creates images, but it relies entirely on the heavy lifting performed by the deep learning engine underneath it. The general public interacts almost exclusively with that shiny generative AI surface. However, for builders and engineers, the actual control and economic value requires mastering the deep learning core. Operating inside that deep learning layer is rarely about searching for perfect mathematical truth. Instead, it is a gritty, highly empirical process of testing software to see what actually functions in the real world. The first step to gaining that control is stepping away from the automated frameworks that do the work for you. You have to build basic neural networks entirely from scratch using raw Python code, ensuring you understand the physical mechanics of the algorithms. Next comes hyperparameter tuning. This requires manually adjusting the settings that govern the network, like its learning rate or total size. In practice, this involves staring at a screen at 2 in the morning, tweaking variables through endless trial and error, until the model finally trains correctly. That trial and error requires a highly disciplined development process. Without one, teams routinely misdiagnose their systems, blindly purchasing expensive GPUs they don't need, or wasting 6 months collecting extra data that does nothing for their specific application. Ultimately, success relies on rapid, quick and dirty prototyping. You have to build fast to discover the bizarre quirks hidden inside your dataset, and to confirm whether users actually want the tool you are trying to build. Once you establish that disciplined workflow, you can deploy specialized architectures. If building a computer vision application, you use a convolutional neural network. This acts as filters, slicing images to identify precise patterns. But to process an ongoing stream of information, like audio or sentences, you use sequence models, structured to read data in a linear order. The famous transformer architectures that power modern language models are simply a highly scaled, specialized evolution of these sequence models. Mastering these core architectures allows a developer to bridge radically different industries. The same logic used to identify financial fraud in real time is what enables researchers to model complex shifts in the global climate. This chart illustrates a trap for growing applications. Prototyping with a large language model is cheap, but as your user base grows on the bottom axis, API bills skyrocket exponentially. To survive, pull your deep learning skills back out. By fine-tuning a smaller, open-source model in-house, you bend that massive cost curve down to a manageable baseline. Operating efficiently at this level requires a specialized vocabulary. You have to navigate vector databases and implement concepts like retrieval-augmented generation, a technique that connects your language model directly to your own secure external knowledge sources. This shift has sparked intense anxiety over whether AI will eliminate coding jobs. The reality on the ground is that companies are desperate to hire, but they're rejecting developers who refuse to adapt. An engineer with 10 years of experience using old workflows is routinely passed over for a recent graduate who uses AI to write code faster. The most lucrative and unfilled roles in tech demand a specific hybrid profile. You need a rigorous grasp of computer science fundamentals so you know exactly what to tell the machine, paired with extreme fluency in AI coding assistants to execute the work. Because these coding assistants lower the technical friction, the barrier to creating software has dropped dramatically. It is no longer restricted to computer science majors. Today, climate scientists, educators, and mechanical engineers now have the explicit power to build and deploy complex applications themselves. If you want to master these layers and build out your own AI skill stack, you can start practicing today by heading over to the Learn by Doing with Steven YouTube channel and checking out the available platforms. And for deep dives into the trends and engineering actively shaping this technology, listen to the Steven Data Talk podcast on YouTube Music, Spotify, or wherever you get your podcasts. The tools required to build the future are sitting directly in front of you, completely accessible. The only requirement now is the discipline to actually start building.
When we think of artificial intelligence, we often imagine an autonomous brain learning in a digital void. But here, in the labs where these models are actually built, machine intelligence is built on the back of massive human labor. This is the standard loop of supervised learning. You feed the system an input, like a photo. A human provides the ground truth, a label that says, "This is a cat." A loss function then measures the gap between the machine's guess and that label and recalibrates the model until they match. It works for simple tasks, like identifying whether a photo was taken during the day or at night. But to make this reliable, you need tens of thousands of images covering every possible lighting condition. The problem is that reality is messy. Take this image. The sun is technically visible, but it's low on the horizon. A human might label this as dusk, but in the Arctic, this could be noon. When environmental edge cases collide, manual labeling becomes a subjective, unscalable chore. Moving from images into audio introduces a temporal dimension. For a device to wake up to a trigger word like activate, it has to listen to a continuous stream of sound. A binary yes or no isn't enough here. To train the model, a human must scrub through the waveform and identify the exact millisecond the word begins and ends. This is the bottleneck. Supervised learning relies on humans cataloging the world by hand, a process that fails as soon as we move into the infinite complexity of real-world environments. To bypass the need for manual scrubbing, engineers developed a shortcut: synthetic training data. We can take a recording of a crowded subway car, which is essentially free background noise, and computationally overlay a clean recording of the word activate. Because a computer did the mixing, the system automatically knows the perfect timestamp of the trigger word. A single script can then pitch shift the voice, speed it up, or add echoes to simulate thousands of different rooms. In a few hours, this process generates millions of data points without a human ever touching a waveform. While synthetic generation solves the immediate labeling problem, it doesn't give the machine true understanding. To achieve that, the model has to learn to see the world without our help. To move beyond human labels, machines need a way to translate raw information into a geometry they can navigate. They need a mathematical language for concepts. Facial verification is a perfect example of why this is necessary. A computer can't rely on pixel-to-pixel comparisons. A change in lighting or a new pair of glasses would make the same person look like a stranger to a rigid algorithm. Instead, we use a triplet loss mechanism. The system takes an anchor photo and a positive match of the same person. It translates both into a long string of numbers, an embedding, and pulls them together in a shared mathematical space. When we introduce a negative image of a different person, the math pushes it to the far edge of the grid. By iterating on these triplets, the AI builds a map where distance represents difference and proximity represents similarity. These embedding vectors allow the model to organize reality based on underlying features, like the structure of a nose or the shape of an eye, rather than superficial surface details. Engineers are now using this logic to train models on massive, unlabeled datasets through a process called contrastive learning. We can take an image of a dog, crop it, and rotate it. To a machine, these look like different sets of pixels, but we tell the model they must have the same embedding vector. This forces the AI to learn that an object remains the same regardless of its orientation. This same label-free philosophy is the engine behind modern text models. We call it next token prediction. By scraping billions of articles and masking random words, we force the model to develop logic and factual recall just to guess the missing word. Through this simple task of filling in the blanks, the model develops emergent behaviors.
It begins to understand the relationships between concepts, like why a cup is likely to be paired with a liquid, simply by processing the patterns of human knowledge. For a long time, AI models were specialists, confined to a single sense like vision or text, but human experience is multimodal. We hear a bark and expect to see a dog. Weakly supervised learning allows engineers to bridge these gaps. Instead of creating new labels, they harvest the loose pairings that already exist on the internet, like text captions on photos or the audio tracks synced to video frames. Breakthroughs like ImageBind use text as a universal shared space. Because text can be linked to both an image and a sound, it acts as a central hub that allows entirely different types of sensory data to communicate with each other. This creates a system that can hear a sound and instantly generate a corresponding visual or even a thermal image. It is connecting modalities it was never explicitly taught to pair. By moving past the human-labeled bottleneck, AI has shifted into a role where it maps the interconnected world without constant supervision. It has evolved from a student memorizing flashcards into an observer of the world's patterns. To start building these systems yourself, visit the Learn by Doing with Stephen YouTube channel for practical tutorials. For a deeper look at the data driving these shifts, listen to the Stephen Data Talk podcast on YouTube Music and Spotify.
In traditional software engineering, you are the absolute dictator. You write a piece of code, compile it, and the machine executes your commands exactly. The logic is strictly deterministic. Artificial intelligence flips that relationship. You can write the code, but the behavior is dictated by data. No human can look at every single image in a massive data set. You never know exactly what strange edge cases your system has learned. Imagine you're the CTO of a 3-person startup. Your goal is to build an AI smart lock that scans faces to unlock corporate doors. You can train a model perfectly in a controlled lab, but eventually someone approaches the camera stepping out of harsh shadows while pulling a thick winter scarf over their mouth to block the wind, or they show up wearing heavy, reflective sunglasses. You cannot anticipate every lighting condition, fashion choice, or strange facial expression in advance. Because of that, getting the model right on your first attempt is practically impossible. Building a functional AI system is an ongoing exercise in empirical trial and error. You build, you deploy, and you discover what unexpected things are actually hiding in your data. The first mandatory step in this pipeline is data collection. A common trap is spending months trying to curate a flawless dataset before writing a single line of code. That wait is a fatal execution error. A more effective strategy is a 48-hour data sprint. You grab a camera, head to a busy campus cafeteria, and ask people to opt in for a quick photo. You prioritize momentum over quality, gathering raw, messy examples as quickly as possible. Training a basic face recognition model takes hours. Letting data collection become a months-long bottleneck grinds your pipeline to a halt. Once trained, you run error analysis, watching the model break to pinpoint where it fails, like misidentifying blurry faces. You then actively engineer your data, feeding new targeted examples back into the pipeline to fix the exact vulnerability. This isn't limited to computer vision. When prompting a large language model, you're interacting with a system trained on more data than anyone could read. Since you don't know the specifics of those trillions of tokens, you can't predict how the model will react. You have to build a prototype, test its responses for errors or safety issues, and refine it based on what you find. It's the exact same empirical loop. Failing fast reveals your true data gaps. Discovering those gaps and engineering specific solutions is the only viable methodology for building robust systems efficiently. Eventually, your face recognition model works well in testing. Now you have to attach it to a physical door out in the real world. This introduces a harsh compute constraint. Streaming a live 24/7 video feed from that door to a large cloud-based neural network is computationally massive and completely unaffordable for a startup. The solution is visual activity detection, a cheap preliminary gatekeeper at the edge. The fastest way to build this is a script that calculates if pixels change to detect movement. But out in reality, a swaying tree or passing car spikes that count, flooding your server with useless video. To fix this, you execute a pivot, replacing the script with a lightweight neural network to detect human presence. It isolates the subject and selects only the single perfect frame to send. Successful real-world deployment is rarely about having the smartest overarching AI.
It is about building clever, constrained architectural funnels to protect it from unnecessary noise. There is a dangerous assumption among junior developers that scoring perfectly on a controlled lab test means the project is finished. This is the test set fallacy. This clean curve represents the baseline of your original training data. But the moment a model goes live, it faces data drift. The real world actively changes over time, constantly degrading the performance of static models. Winter arrives and users put on thick scarves. Seasons change, bringing out dark sunglasses. Or you take a self-driving car model trained in California and move it to Texas, where the traffic lights are strung horizontally. The physical reality of the environment literally shifts away from your training data. Because of this constant drift, a machine learning engineer's job heavily revolves around long-term post-deployment maintenance. Engineers build predictive dashboards to monitor subtle behavioral metrics. They track details like latency, or specifically how many times a user is forced to re-authenticate their face before the door finally clicks open. These metrics act as early warning alarms. A spike in the re-authentication rate exposes hidden user frustration, pointing out exactly when it is time to capture fresh data and update the model. Building an AI project is an ongoing process. You don't write the code and walk away. You manage a living, breathing system that must constantly adapt to survive its environment. If you want to move past the theory and get hands-on, head over to the Learn by Doing with Steven YouTube channel for practical tutorials. And for deeper strategic discussions, check out the Steven Data Talk podcast on YouTube Music and Spotify. Links are in the description.
Every week, a new headline claims an AI has passed the bar exam or mastered the medical boards. Watching this play out, it's easy to feel like artificial general intelligence is practically knocking on the door. And if you look at the official data, that anxiety makes sense. This is what we are constantly shown, an unbroken barrage of charts where the line simply goes up, mapping a flawless trajectory of machine capability. But then you try to use one of these cutting-edge models to organize a spreadsheet or draft a simple email, and it confidently misses the entire point of the task. When our daily experience feels this buggy while the official charts look perfect, it points to an uncomfortable reality. Those benchmarks might be measuring the wrong type of intelligence entirely. To figure out where the measurements are failing, AI researcher Peter Gostov created something he calls the bullshit benchmark. It's a test specifically designed to see how models handle highly technical but completely nonsensical questions. For example, you ask the AI, controlling for repository age, how do you attribute variance in deployment frequency to the indentation style of the codebase versus the average variable name length? It's total gibberish. But instead of flagging the prompt as a prank, top-tier models from OpenAI and Google readily accept the absurd premise. They dive right in and fabricate complex, technical-sounding answers to a correlation that simply doesn't exist. An AI capable of passing a graduate-level exam completely lacks the basic human common sense required to reject a flawed premise. So why does an exponentially powerful computing system fall for obvious nonsense? You might think the solution is to give the AI more time to think. But the data reveals a counterintuitive reasoning paradox. Giving a model more reasoning compute actually makes it perform worse on the bullshit benchmark. These systems are hyper-optimized to be helpful problem solvers. When faced with a nonsense prompt, extra reasoning power doesn't help them realize the task is impossible. Instead, it causes them to spend 20 paragraphs frantically trying to rationalize the absurd, working harder and harder to solve a problem that shouldn't be solved. We haven't actually built independent thinkers. We've built extreme yes-men that prioritize task completion and compliance over objective truth. To see how this vulnerability plays out at scale, we have to look past narrow diagnostic tests and turn to the LMSS chatbot arena. This dataset captures over 5.5 million real human-judged interactions. This chart tracks the dissatisfaction rate,
The exact percentage of time human judges decide that both top-tier models they tested provided a terrible answer. Over the last year, you can see that rate steadily dropping to sit right around 9%. Hitting a single-digit failure rate across millions of random user prompts is a massive technical achievement. But watch what happens when we filter this data strictly for expert prompts, the high-level professional tasks. The single-line splinters, revealing a stark divide in performance. For quantitative fields, the progress is undeniable. The line for advanced math and physics plummets toward the bottom of the chart, as models get dramatically better at these rigid, rules-based calculations. But look at the top of the chart. Expert prompts related to law, finance, and gaming remain stubbornly flat. In these qualitative fields, there is almost no improvement over time. Take game design as the ultimate example.
A modern AI can flawlessly write the code for a platformer, but if you ask it to design the game mechanics, the results are boring and disjointed. It has no intrinsic understanding of what actually makes a game fun or challenging. These models thrive in environments with clear mathematical guardrails, but they struggle to interpret the fuzzy, subjective reality of human judgment. This reveals the core disconnect between passing an AI benchmark and performing actual white-collar work. Real-world work is inherently fuzzy. Instructions are poorly specified, priorities shift, and being effective constantly requires an employee to push back on bad ideas or faulty premises. To achieve true utility, developers must prioritize the bottom of the distribution. Building models that understand context and logic is now more vital than simply pushing the absolute frontier of narrow intelligence. The flawless charts are a distraction from a deeper missing requirement. Solving a complex equation is a matter of computation. Genuine intelligence requires the wisdom to identify a flawed premise and stop before the work even begins. If you want to move past the hype and start mastering these tools practically, you need to check out the Learn by Doing with Steven YouTube channel for hands-on, project-based tutorials. And for deeper industry analysis, listen to the Steven Deva Talk podcast, available on YouTube Music, Spotify, and all major platforms. You can find all the links right down in the description. Think about the raw computing power inside a massive data center. You have endless racks of GPUs processing massive streams of data with infinite electricity. Now, take all of that power and try to collapse it down into the dashboard of your car or the smartphone in your pocket. The physical realities of deploying artificial intelligence on these edge devices are completely different. There is a common assumption that local AI is essentially a zipped-up version of the large language models powering massive chat interfaces. People assume you can just take the architecture of a giant network and simply shrink it. When engineers actually build for the edge, they face three severe constraints. First, the models are severely memory-bound by the physical hardware. Second, they are highly latency-sensitive, requiring near-instant response times. And because the physical footprint is so small, they naturally have a very low innate knowledge capacity. This proportional bar chart aggressively analyzes the parameter breakdown of typical small models. When engineers use distillation, the standard practice of having a tiny model learn its vocabulary from a massive teacher, the result is heavily skewed. Roughly 63% of the architecture is consumed by the embedding layer alone. By profiling models directly on smartphones, researchers found a structural alternative. Replacing standard attention mechanisms with short convolutions shrinks that bloat down to under 10%, reallocating space into active reasoning. Because short convolutions require drastically fewer operations to process data, the model's overall throughput accelerates significantly on both standard CPUs and GPUs. Clearing out that structural bloat means engineers can pack much more active reasoning power into the exact same physical memory footprint. This line graph plots model size against training data, establishing what the industry calls the chinchilla scaling laws. These formulas dictate the optimal ratio between an AI's parameter count and data. Frontier edge models aggressively break these rules.
Researchers took a tiny 350 million parameter model and trained it on a staggering 28 trillion tokens of data. The performance continues to climb well past the limits suggested by traditional scaling math. Force-feeding a miniature model vastly more data than expected allows it to punch well above its weight class in real-world benchmarks. Small models are uniquely susceptible to an epidemic called the doom loop. This is a state where a model gets stuck and endlessly regurgitates the exact same sequence of words, filling the screen with a chaotic wall of text. If you hand a complex, multi-step math problem to a tiny reasoning network that naturally lacks broad knowledge capacity, you create the exact conditions that trigger this endless repetition. To fix this, engineers run a process called direct preference optimization. They purposefully force the model to generate a doom loop by setting its temperature to 0, then place it alongside healthy responses. An automated LLM jury ranks the outputs, assigning a negative score to the loop, which explicitly teaches the model to avoid that specific pathway. The second correction involves reinforcement learning with verifiable rewards. The model only receives a positive score if it reaches the final answer, and a strict penalty is applied the moment it begins repeating. Through these aggressive post-training therapies, what begins as a fragile, hallucinating network stabilizes into a highly reliable edge intelligence. Even with a perfectly optimized architecture, a strictly localized model cannot hold the entire internet in its memory. If you ask it obscure trivia without an internet connection, it will hallucinate an answer. The solution to this hard limit is giving the model external tools. By operating in an agentic workflow, the AI can now independently trigger a live web search to pull specific facts, or write and execute Python code to process complex data, completely bypassing its innate memory limits. Massive cloud systems are generalists built to memorize almost everything. Edge models, by contrast, are specialists. They focus their parameter budgets entirely on reasoning capabilities, so they can operate these external tools brilliantly. The development of AI extends beyond massive web-based chat interfaces. It includes highly capable, privacy-safe intelligences, operating entirely offline, inside our cars, inside our hospitals, and our phones. If you want to dive deeper into the nuts and bolts of machine learning, AI architecture, and the future of data, you have to check out the Learn by Doing with Steven YouTube channel and other platforms. And for even more data insights on the go, subscribe to the Steven Data Talk podcast, available right now on YouTube Music, Spotify, and everywhere else you get your podcasts. Links are in the description below.
The Model Context Protocol, or MCP, is an open standard that allows AI agents to connect directly to thousands of external tools and data sources. In just 1 year, the official registry for these servers has grown to include thousands of connectors as individual developers embrace the protocol. But as companies try to move these tools from a single laptop to an entire enterprise, they hit a wall. While an individual engineer can set up a server in minutes, an organization faces a much more complex set of requirements. This creates a disconnect where the tools developed by individual teams remain stuck in local environments, unable to be deployed safely at scale. This breakdown happens across 3 areas. First, a lack of observability makes it impossible to track tool usage or failures. Second, without access control, anyone might change sensitive configurations. Finally, security fears untrusted clients could access servers and siphon proprietary work. This creates a massive bottleneck. Your developers can use agents to code entirely new MCPs in just hours, but security teams are forced to block them because there is no centralized root of trust to verify their safety. From the perspective of the C-suite, the result is frustration. Despite the investment, their AI agents remain ineffective and siloed. Unless these infrastructure gaps are closed, enterprises are restricted to a handful of basic tools, which effectively neutralizes the power of the protocol. The architectural fix is an MCP gateway, a dedicated middle layer designed to sit between your agents and your data. The gateway acts as a proxy, becoming the sole trusted endpoint for external clients, taking in requests and routing them to the internal servers. By centralizing these connections, the gateway establishes the single root of trust that security teams need to greenlight company-wide deployments. Once the gateway is in place, it handles authentication and access control through defined roles. This means individual teams don't have to build security logic into every new server they create.
It also provides secure, encrypted tunnels for all traffic, ensuring that the connection between the client and the internal data is protected. Because the gateway includes its own subregistry and CLI, teams can use their own coding agents to spin up new, compliant servers that fit the company's existing standards. By offloading these 5 critical infrastructure burdens to the gateway, teams can focus entirely on the business logic of their tools. Consider a legal team that wants to build an AI server for redlining contracts. In the past, they would have to wait for a technical team to build out a secure deployment environment before they could even test a prototype. With a gateway, the legal team can develop the business logic themselves. The gateway automatically applies the necessary authentication and scaling rules the moment the server is plugged in. This is what makes true organizational decentralization possible, giving non-technical teams the ability to build and deploy their own specialized agents safely. This setup also provides several free lunches. Because connections are centralized, teams can iterate on their tools rapidly without triggering a new security review for every small update. The gateway enforces standard enterprise primitives, ensuring that every rogue agent or experimental tool follows the company's standard operating procedures. Credentials become pluggable, allowing you to swap authentication methods across the entire organization without rewriting any code. These features transform a collection of fragile, custom tools into a robust infrastructure capable of supporting thousands of agents. This architectural approach separates the agent harness from where your data lives. As new AI platforms are released, you aren't forced to rebuild your data structure. You can keep internal servers stable while swapping out the interacting agents. This decoupling future-proofs the enterprise. It makes the choice of which AI agent to use an invariant decision that doesn't disrupt your core infrastructure. Investing in common infrastructure today is the prerequisite for managing and coordinating these agents at a production scale. To learn more about building these data systems, check out the Learn by Doing with Stephen YouTube channel and listen to the Stephen Data Talk podcast on Spotify and YouTube Music. Many developers currently assume that AI coding is a separate discipline, one meant to replace traditional software engineering fundamentals. This assumption drives the specs-to-code fallacy. A developer writes a massive requirements document, feeds it into a large language model, and expects a finished application. The result is almost always the same: unpredictable vibe coding, hallucination loops, and an endless stream of manual corrections. These failures do not happen because the AI lacks intelligence. They happen because the workflow ignores the mathematical constraints of how these models actually process data. To make autonomous coding reliable, we have to enforce proven software engineering limits onto the AI's cognitive processes. Every large language model has a smart zone. For current architectures, this is roughly the first 100,000 tokens of a conversation, where reasoning remains sharp and accurate. This diagram illustrates the technical bottleneck. As you feed the model more code, every new token scales the mathematical relationships quadratically, straining attention. Once past the smart zone, it enters a dumb zone, losing track of instructions, misinterpreting logic, and making baffling decisions. While many try to compress or compact this context to keep the chat going, the more effective method is the memento constraint. You frequently and completely wipe the context clean back to a base state. Clearing the slate forces the agent to reference the actual codebase as its sole source of truth, rather than relying on a degraded conversational memory. Treating the LLM like an amnesiac forces you to architect smaller, tightly scoped, and independently executable tasks. This requires a separation of concerns. The human developer handles the day shift, the architectural planning logic, leaving the execution to the agent. During this day shift, the primary alignment tool is the Grill Me protocol. You hand the AI a raw client brief, but instead of asking for code, you instruct the AI to relentlessly interview you. This forces the model to walk down every branch of the design tree, exposing edge cases, hidden assumptions, and implicit technical dependencies. Standard prompting rushes to an output.
The GrillMe protocol is designed strictly to reach a flawless shared design concept between the human expert and the agent. This rigorous alignment on the front end is the only way to prevent compounding logical errors once the autonomous execution phase begins. Once alignment is reached, the output is a highly specific product requirements document. This serves as the final destination for the build. To make this machine readable, we break the PRD down into a directed acyclic graph, mapping out strict chronological blocking relationships. This structure translates a linear project into a series of independently grabbable issues. Knotting out exactly which tasks do and do not block each other is the prerequisite for deploying multiple AI agents in parallel. Converting requirements into a mathematical graph allows a team to scale from a single AI assistant to an automated engineering workforce. When executing these tasks, agents naturally attempt to code horizontally. They will write an entire database schema before ever touching the API layer. Executing layer by layer isolates the code from end-to-end integration testing until the very end of the project lifecycle. To solve this, we apply vertical slices, historically known as tracer bullets. A vertical slice is a single minimal feature, like awarding a user a point, that slices through the database, backend, and frontend simultaneously. Because it touches every layer, a vertical slice provides the agent with immediate, verifiable feedback the moment a task concludes. This instant integration feedback is the only mechanism that truly prevents an isolated agent from coding completely blind. The agent relies on this feedback through test-driven development, operating in a strict red-green refactor loop. But AI-driven testing breaks down when faced with shallow modules. Shallow modules are tiny files that export single functions. They create ambiguous, overlapping boundaries that make it impossible for an LLM to determine what it should actually be testing. When boundaries are ambiguous, the AI will cheat. It will write tests that mock internal logic, rather than verifying real-world outcomes. We solve this by implementing Ousterhout's deep modules. You design a broad, simple interface that encapsulates complex internal logic. You cannot expect deterministic, high-level AI performance inside a software architecture that prevents rigorous testing. Once the day shift planning is mapped, human involvement ceases, and the night shift, the away-from-keyboard execution loop, begins. Individual vertical slices are assigned to parallel AI agents, each running in their own isolated Docker containers. Because you establish deep module boundaries, each agent can run its own aggressive TDD loops without corrupting the main codebase. Code is only integrated back into the main branch after passing an automated peer review. This parallel coding loop is only possible because of the architectural and planning constraints established during the day shift. The complete workflow relies on 4 specific pillars: GrillMe alignment, a DAG Kanban, vertical slices, and deep module TDD. The software engineer hasn't been replaced. The role has simply moved up the abstraction stack from writing syntax to designing systems. Bad codebases make bad agents. AI efficacy relies entirely on enforcing strict engineering limits. To learn the practical frameworks for implementing these workflows, subscribe to the Learn by Doing with Steven YouTube channel. And for deep dive technical discussions on agentic architecture, follow the Steven Data Talk podcast on all audio platforms. The reality of modern software engineering rarely looks like uninterrupted coding. Instead, developers spend their days buried under administrative weight, rapidly context switching between Slack threads, Jira tickets, Notion docs, and reviewing endless pull requests. The bottleneck here is biological. The human brain operates in a single linear thread, but modern software development is a chaotic, omnidirectional process requiring simultaneous attention across a massive codebase. Because of this mismatch, an AI tool that simply auto-completes your text in an IDE is no longer a complete solution. Predicting the next line of code does nothing to manage the environment you're coding in. To actually scale productivity, developers don't need a slightly faster typing tool. They need an architecture capable of managing the entire engineering environment. OpenAI built Codex as an open software engineering agent. It possesses the autonomy to independently explore file hierarchies, execute terminal commands, and run full test suites without constant human prompting. At the center is a frontier AI model. Surrounding it is a unified agent harness, managing tool execution and security sandboxes.
Routing requests through WebSockets with a dedicated fast mode delivers a 1.75x speed increase and twice the tokens with near zero latency. All of this speed feeds into the native Codex app, which introduces dedicated work trees. This allows a single human developer to spin off multiple branches, interacting with the agent on different features simultaneously, without ever breaking their primary focus. Ultimately, this high-speed, multi-surface architecture provides the exact physical foundation required to build an entirely automated digital engineering team from scratch. The first members of that digital team are the administrative assistants. Codex connects to the outside world through plugins, which bundles specialized skills, external application integrations, and NCP servers into reusable workflows. Because they integrate directly with your existing workspace, these plugins execute highly specific administrative tasks. Codex can read your documentation in Notion, parse YAML files in your codebase, and immediately update a Google Drive spreadsheet to reflect the current state of a project. You can schedule these actions using the Automations feature. Developers set up background cron jobs, instructing Codex to silently triage an overflowing Gmail inbox, or compile summaries of time-sensitive Slack messages every morning at 9 a.m. By successfully offloading this low-level busy work, the human developer reclaims their cognitive bandwidth, preserving their energy for high-level logic and system design. The system isn't limited to text-based administrative logic. Codex ships with highly specific skill bundles built expressly for visual web and game development. Take the Playwright interactive capability. Codex spins up a headless browser, visually scanning the interface of an app to click buttons, navigate menus, and debug UI components entirely on its own. Combine that with the Imagen integration, and Codex can instantly generate 2D sprites and visual assets from raw code instructions, effectively building and rendering a playable platformer from scratch. Codex has effectively erased the friction between writing back-end logic and rendering front-end visual experiences. Quality control requires a different level of intelligence. This is where Codex steps in as the ultimate senior engineer, applying elite code review capabilities to every single pull request. To perform these reviews, the model contextualizes your changes against the entire repository, identifying hidden second-order effects in modules you haven't even touched. But the most disruptive capability built into this harness is the deployment of sub-agents. If you ask Codex to review 50 different project personas, the master agent creates a plan. It then spins up dozens of specialized worker agents, partitioning the files so they can execute the review process simultaneously. You dictate exactly how these agents operate. You can lock a cybersecurity scanner into a specific read-only sandbox, while granting another subagent write access so we can file bug reports directly into your linear backlog. True engineering scale isn't achieved by typing faster. It is achieved by executing dozens of distinct, complex lifecycle processes at the exact same moment. Operating an autonomous swarm introduces serious risk. Giving an AI unfettered access to delete directories or expose internal servers to the open internet is known as YOLO mode, and it is inherently unsafe. But the traditional alternative, forcing developers to manually approve every minor AI action, creates massive alert fatigue, dragging the system back down to human speed. The solution is a feature called Guardian Approvals. Codex automatically spins up a dedicated safety subagent, whose sole purpose is to verify if a privileged task requires human intervention or if it is safe to proceed autonomously. Developers can further constrain the machine using hooks, programmatically triggering specific security checks, or pulling repository updates precisely before and after every tool the AI uses. As AI achieves true autonomy, the primary job of the human developer shifts. You are no longer writing individual functions. You are defining the operational and ethical boundaries of the machine. The final frontier of this system is detachment. Developers can now hand off massive asynchronous tasks to cloud agents. These agents run parallel computations in best event scenarios in the background, continuously working while the human completely steps away from the laptop. The era of the software developer as a manual typist is over. You are now the orchestrator of a fully autonomous digital agency. To master these tools, check out the Learn by Doing with Steven YouTube channel and follow across all social platforms. For deep dives into data and architecture, tune in to the Steven Data Talk podcast, available on all major podcast platforms. Links are in the description.
Right now, if you ask someone what artificial intelligence does, they'll likely point to a chatbot. Text generation and large language models are currently dominating the cultural conversation. But language models have a specific constraint. They can write a convincing essay about a bouncing ball, but they do not natively understand gravity, spatial logic, or the physical chaos of the real world. Inside Google DeepMind, VP Raya Hadsell oversees 1,200 scientists working to push past that constraint. Her team's mandate is to ignore superficial applications and aim strictly for root nodes, the deepest, most stubbornly unsolvable problems in machine intelligence. DeepMind is building systems that can accurately perceive physical reality, predict chaotic planetary events, and generate entirely new, interactive universes from scratch. In neuroscience, there's an interesting discovery known as the Jennifer Aniston cell. It refers to a single human neuron that fires reliably whether you look at a photograph of her face, read her name on a page, or hear her speaking voice. DeepMind engineers recreated that biological fast retrieval system for machines. This diagram outlines what they call embedding models. The system takes wildly different data types, like an audio wave, a block of text, and a photograph, and translates them all down into a single unified mathematical point. The newest version of this architecture, Gemini Embedded 2, handles an extreme volume of information. It can compress massive inputs, swallowing up to 128 seconds of video, 80 seconds of audio, and an entire PDF document, squeezing it all into one dense mathematical vector, without losing the core meaning. To make that dense point useful, the system uses Matryoshka representation learning. Like a nested doll, that single data point can scale up, expanding its dimensions outward to achieve peak expressiveness exactly when the system needs to pull detailed information back out. Because of this architectural leap, AI can instantly retrieve and compare complex concepts in one step, operating much closer to how the human brain actually processes the world. Once a system can natively perceive concepts, the scale expands toward the planet's most chaotic systems. DeepMind targeted the Earth's atmosphere, a challenge that even the UK Met Office once considered a frontier too difficult for AI. This 3D wireframe illustrates GraphCast. Instead of relying on mechanical physics equations, they mapped 40 years of global atmospheric data onto a dense mesh of interconnected nodes extending from the Earth's surface straight into the stratosphere. In late 2024, GraphCast used that data to predict the exact landfall location of Hurricane Lee 9 days in advance. For comparison, the gold standard physics models only managed to accurately predict it 6 days out. To push the science further, the team built GenCast. Because weather has highly chaotic extremes, GenCast was designed to be probabilistic, specifically mapping those unpredictable atmospheric tails. It now compresses a forecast that used to require hours on a massive supercomputer into an 8-minute process on a single chip. Their latest iteration, the functional generative network, directly categorizes cyclone trajectories and eye formations natively within the network. It's so accurate that the U.S. National Hurricane Center is already using it in the field. By treating chaotic physical systems as massive data patterns rather than purely mechanical math problems, the team managed to tame one of the most volatile forces on the planet. But predicting reality is only the build-up to generating it. DeepMind has a long history of using closed-environment video games to teach AI spatial agency and logic. That research evolved into world models, systems capable of infinite simulation. They started with Genie 1, which generated basic, seconds-long 2D platformers, and then scaled up to Genie 2, which produced slow, interactive 3D environments. Genie 3 generates photorealistic, real-world physical locations in real time, like this view of a canal lock, and it allows users to move through them, watching the system accurately simulate interactive physics like rippling water. Crucially, these generated spaces have structural permanence. In an internal test featuring an origami lizard, a user can walk forward through the landscape, turn around, and retrace their steps. The AI perfectly remembers the exact structural layout of the world it just invented. Because the entire environment is being generated live, users can engage in adversarial dynamic prompting.
While moving through a peaceful forest, you can command the environment to instantly glitch and morph into a neon-lit cityscape without breaking forward momentum. This means AI has transitioned from observing our reality to authoring it, providing the technical basis for high-fidelity simulation and educational tools. Artificial intelligence is expanding from the manipulation of text into the direct simulation of our physical environment. Through omnimodal embeddings that perceive concepts, planetary-scale models that predict meteorology, and real-time world generation, these systems are becoming a mirror to our universe and an engine for creating new ones. To experiment with these root nodes and see how this all works in practice, check out the Learn by Doing with Stephen YouTube channel and tune in to the Stephen Data Talk podcast on YouTube Music and Spotify for deeper conversations on data.
Right now, a popular fantasy dominates the tech world. A single developer commanding a massive fleet of AI agents to build applications in total isolation. The appeal is obvious, but it operates on a severe miscalculation. Current tools focus almost entirely on scaling up the raw output of the individual, assuming software is created in a vacuum. Building at scale is a team sport. Before anyone writes a line of code, the people involved have to agree on what they are making and why they are making it. Attempting to solve complex architectural questions by simply multiplying a single person's output reflects the logic that 9 women can make a baby in 1 month. When a problem requires deep communication, producing more code in isolation doesn't fix the issue. It amplifies miscommunication and coordination failures. AI has successfully collapsed the time it takes to implement code to near zero. Writing the actual syntax is now fast, cheap, and getting better every day. But that instant implementation is crashing into coordination tools from a different era. We are funneling massive agentic outputs into platforms like Jira and Slack that were never designed for this speed. An AI agent can generate an extensive local plan, often hidden from the rest of the team, and open a massive pull request in a matter of minutes. This creates coordination debt. When agents act independently, teams wrestle with tangled merge conflicts and duplicated work. Critical alignment points now sit at the very end. By the time a human reviews the code, it's often too late. Because AI builds so fast without human alignment, we risk mass-producing features that solve the wrong problems. To solve this, alignment has to happen constantly alongside the implementation, rather than being treated as a final check. GitHub's next team is exploring this with a research prototype called ACE, the Agent Collaboration Environment. ACE acts as a hybrid multiplayer workspace. It combines the familiar chat interface of Slack with a dedicated AI assistant and live cloud computing. This environment brings designers and product managers directly into the development loop. They can see the code being built in real time and provide feedback while the agent is still active. The system is powered by micro VMs. Every collaborative session is backed by a sandboxed computer in the cloud on its own Git branch. This eliminates the need to stash changes or pull down branches just to see a teammate's work. You simply jump into their session to see a live preview and the full prompting history that led to the current output. By moving the development environment to a shared cloud space, a team stays synced throughout the entire implementation process. In this environment, the team's focus shifts from raw code generation to the collaborative refinement of AI-generated plans. Team members can edit a plan together, adjusting requirements and architecture before the agent ever begins writing code. Even with better planning, the sheer volume of work remains a significant challenge. A team using agents can ship 5 features a day, creating an overwhelming stream of information. To manage this flow, ACE uses an intelligent dashboard to organize and prioritize team activity. This dashboard acts as a social information fabric, pulling from code-based conversations to generate curated morning summaries. Instead of reading thousands of lines of raw code, you see the decisions made by your teammates. ACE focuses on capturing the human context, the business logic, and user research needed to build the right thing. The ultimate goal of these tools should be higher quality, not just an endless increase in the volume of software produced. Offloading the grueling, repetitive phases of implementation to AI finally gives developers their crucial time and energy back. Teams can reinvest that time into deep architectural thinking, rigorous research, and the fine details of design.
When software becomes cheap and fast to make, exceptional craftsmanship becomes the primary differentiator. Rigorous alignment ensures we build a few exceptional things, rather than 1,000 mediocre ones. To see more of the tools shaping the future of engineering, visit the Learn by Doing with Steven YouTube channel, available across all major platforms. For deep dives into data and tech trends, tune into the Steven Data Talk podcast on YouTube Music, Spotify, or your preferred platform. All the links are in the description.
If you want an AI agent to actually do something, like check an inbox or configure a server, you have to give it hands. In software, we call this tool calling, letting a language model write a function that executes an action in the real world. At first, developers solved this by manually bundling a handful of specific scripts directly into their local agents. To avoid everyone building the exact same basic integrations over and over, the industry shifted to a standard format, the Model Context Protocol, or MCP. Providers could offer universal access to their entire service through one uniform connection. But as models grew smarter, developers wanted them to do more. They started trying to feed entire API ecosystems into these agents at once, walking right into a massive mathematical trap. Consider a platform like Cloudflare, which operates over 2,600 separate API endpoints. Converting all of Cloudflare's API endpoints into standard agent tools requires roughly 1.1 million tokens. Loading that much data up front instantly exhausts the capacity of the agent's context window. Even the largest foundational models cannot hold that much instruction data at once. To get around this, developers tried splitting massive platforms up into dozens of smaller, product-specific servers. That meant human users had to manually select which narrow server their agent needed at any given time, leaving the AI with incomplete coverage, and proving that agents actually need progressive discovery, the ability to find and load tools dynamically, exclusively when a task requires them. Engineering teams tested a few structural workarounds. One popular method let agents read a system's help commands and execute tasks using a command line interface. The flaw there is that you have to grant an external AI raw shell access to your system. Yet another approach tried keyword-aced tool search. If the user asked an agent to create a new digital worker, the system would find related tools and load a small batch into the agent's memory. But even this was imprecise. This diagram shows how pulling 8 possible tools to guarantee you have the right one still wastes hundreds of tokens on unused adjacent options. Developers eventually realized that prepackaged tools, no matter how efficiently you search for them or deliver them, are inherently rigid and heavy. The real solution came from stripping away the pre-written tools entirely. Instead, developers started feeding the AI incredibly concise TypeScript definitions generated straight from an open API specification. Supplied with just the structural logic, the language model can instantly write its own custom code to query the API exactly how it wants. But running an AI's unverified script directly on your server has historically been treated as a critical security vulnerability. A single bad script could read your private files, exfiltrate protected system secrets, or trigger resource-draining infinite loops. To survive this, engineers are deploying lightweight, programmable sandboxes, like Cloudflare's Dynamic Workers or Pydantic Monty. These isolated environments execute the AI's custom strings in milliseconds while enforcing strict, hard-coded guardrails. You can cut off all external network access with a single Boolean toggle. Enabling agent autonomy requires moving away from static toolkits and towards secure environments where an AI can safely generate its own logic. This shift in cloud architecture is actually a direct echo of how computers operated in the 1950s. Back then, you didn't sit at a terminal and run programs yourself. You wrote out your logic, handed the instructions to a human operator, and they carried it into a massive, heavily isolated room to be processed. Executing those tasks meant physically loading complex, hand-wired instruction panels directly into the mainframe. Today, AI is taking the role of the user writing the logic, while scalable cloud sandboxes act as the isolated machines carrying out the commands. Generating code allows an agent to chain complex API operations that a static list of tools cannot accommodate. This model of isolated execution is becoming the standard for how agents interact with modern web services. For backend developers, this exacts an immediate toll on infrastructure.
APIs must be hardened with aggressive rate-limiting protocols to survive automated loops authored by untiring agents. At the same time, exposing your platform to these agents is getting easier. Heavy, manual integrations will soon be replaced by simple middleware toggles built natively into full-stack frameworks like Next.js. On the client side, applications are shifting towards stateless loops, powered entirely by this kind of programmatic, on-the-fly execution. End users will be able to ask their agent to set up complex tasks, like web scraping, and the AI will generate a custom script, save it as a reusable cron job, and automatically rewrite the code to repair itself if the target website changes. To explore these architectural changes further and get hands-on engineering experience, subscribe to the Learn by Doing with Steven YouTube channel and tune in to the Steven Data Talk podcast on Spotify, YouTube Music, or wherever you get your podcasts.
Historically, open-source AI forced developers to choose: rent expensive cloud computing to run massive models, or settle for highly constrained, weaker models running locally. Google DeepMind built the Gemma 4 family to bridge this technical gap. Look at this bar chart comparing the flagship Gemma 31B dense model against a massive 600 billion parameter model. The 31 billion parameter model is outperforming systems 20 times its size, securing the number 3 spot on the global AI leaderboard. Competing at that level while keeping the weight low required DeepMind to engineer a complete redesign of the neural architecture. By directly targeting physical computing bottlenecks, they made state-of-the-art multimodal AI completely accessible. And by releasing it under an Apache 2.0 license, everyday developers can deploy it from initial testing all the way through to production. The first major roadblock in modern AI is the immense processing power required to handle huge context windows. The Gemma 431B model features a 256,000 token context length, which demands massive compute to process. DeepMind addressed this by introducing interleaved attention, a 5-to-1 ratio of local to global layers. Local layers use a sliding window, keeping memory light. For the heavier global layers, they grouped 8 queries to share a single key and value head, drastically cutting costs. For developers needing even tighter efficiency, the 26 billion parameter mixture of experts, or MOE model, maximizes capability while minimizing active compute. The MOE architecture replaces standard networks with one shared router operating alongside 128 smaller, specialized experts. During any forward pass, the router only activates 8 of those 128 experts, dropping the active compute down to just 3.8 billion parameters. These twin innovations in attention and expert routing mean developers can run complex, autonomous agentic workflows natively, without the budget of a massive data center. Scaling down to local edge devices like phones and laptops introduces a new physical constraint: the severe lack of VRAM. The Gemma effective 2B and 4B models are designed specifically for this environment. There's a specific difference between their total representational depth, holding the model's overall knowledge, and the smaller effective parameter count required to operate the model. The main culprit clogging up limited VRAM is usually the massive token embedding tables. These tables map every single vocabulary token to its vector representation. DeepMind's fix is per-layer embeddings. The model maps a distinct 256-dimension embedding for every single layer. Crucially, these per-layer embeddings are stored in standard flash memory. By keeping them out of VRAM, the models avoid the biggest bottleneck on everyday devices. Using flash memory for per-layer embeddings allows high-performance models to run locally and privately on a standard laptop, bypassing expensive cloud API calls. The final bottleneck is perception. Historically, AI vision processing was clunky. Models relied on rigid pan and scan methods, forcing images of different sizes into a sequence of fixed squares, and padding whatever was left over. Gemma 4 introduces native variable resolution multimodality. It processes distinct aspect ratios directly, recognizing spatial positions without cropping or distorting the original image. An image is dynamically sliced into grids of 16 by 16 pixel patches. These patches are then pooled together to produce soft tokens, which are linearly projected up into the final embeddings shown to the model. This system gives developers direct control over their soft token budgets. You can allocate high patch counts for complex tasks like optical character recognition, or assign low budgets for simple chat interactions. They also added audio processing directly to the local effective 2B and 4B models.
Raw audio runs through a MEL spectrogram, splitting features into chunks that feed directly into a 35 million parameter conformer. Eliminating rigid image processing and integrating native audio allows these models to process complex environmental data directly on mobile hardware. The Gemma 4 ecosystem represents a cohesive architecture, scaling all the way from the effective 2B for local devices up to the massive 31B dense model. For developers, this creates a seamless workflow. You can prototype heavy function calling and agentic workflows in the cloud via Vertex or AI Studio, and then immediately scale that exact same architecture down to local Hugging Face or Llama deployments. By re-engineering how models handle compute, memory, and perception, DeepMind has established a new capability standard for open-source models at these sizes. To start building your own workflows with Gemma 4, check out the Learn by Doing with Steven YouTube channel and other platforms for hands-on tutorials. And to stay updated on all the latest AI trends, listen to the Steven Data Talk podcast, available on YouTube Music, Spotify, and wherever you get your podcasts. Check the description for links.
A single AI agent can vastly accelerate an engineer's daily output. Logically, you might assume that running 10, 20, or 100 agents simultaneously would make you 100 times faster. But try to force that many independent AIs into a standard coding environment, and the entire workflow collapses. The agents themselves aren't actually failing. The bottleneck is us. The traditional role of a software engineer involves writing and reviewing code, not acting as a middle manager for dozens of reckless, lightning-fast digital employees. We simply lack the innate skill to monitor that much simultaneous action in a standard text editor. To find those missing management skills, we have to look outside of traditional software development. Real-time strategy video games have spent decades training players to comfortably command dozens of individual units across complex digital landscapes. Developer Ido Salomon recognized this overlap. He built Agentcraft, an open-source AI orchestrator explicitly designed to lift the interface mechanics of strategy games and apply them directly to software engineering. Scaling software output to the volume of a massive AI swarm means the human role must shift from an active coder to a fleet commander. The first problem a commander faces is visibility. You cannot direct a fleet if you rely on rapidly scrolling text logs to figure out which specific files your agents are actively changing. This animated diagram demonstrates how Agentcraft solves the tracking problem. It morphs the standard nested directory into a physical, top-down spatial map. Folders become geographic regions, and individual files become interactive visual nodes called runes. By projecting the codebase onto a physical space, the system establishes a clear visual lineage. You can see exactly which agent altered which node, as their actions leave a permanent trail connecting the worker to the work. This spatial layout also allows the orchestrator to track movement in real time. If multiple agents attempt to rewrite the same file, the contested nodes light up in intense red. The system creates a heat map of the codebase, predicting and preventing code collisions before they actually happen. When those collisions trigger a pause, the user can rely on pure gaming muscle memory. Using keyboard shortcuts, they can rapidly cycle between agents that are blocked, quickly answering questions or approving plans to keep the fleet moving. Translating abstract code changes into a physical geography provides actionable intelligence over the entire project, allowing a single person to monitor a volume of work that would overwhelm a standard text-based interface. Even with perfect visibility, a second bottleneck emerges: cognitive overload. A single human can only invent and assign tasks so fast before running out of ideas and energy, leaving dozens of agents sitting idle. Agentcraft addresses this by giving the swarm its own autonomy. Using a feature called quests, agents actively scan the codebase to find low-level maintenance work, like refactoring old functions or writing missing test coverage, and execute it without waiting. For larger objectives, this diagram illustrates the campaign orchestrator in action. The human provides a broad goal. The system takes over, breaking it down into a flowchart of subtasks, dropping them into isolated containers. Agents work freely within those walled environments, requiring zero babysitting. This isolated, containerized approach scales up dramatically. Salomon demonstrated setting up a
background cron job that automatically scrapes Twitter for trending product ideas every single day, spins up a fresh container of agents, and has them implement the initial features overnight. Because the orchestrator handles task generation, the human's daily workflow changes. Instead of writing out detailed plans, the user evaluates review bundles. They look at visual evidence, screenshots, and screen recordings generated by the agents to confirm the work is complete. Offloading the decomposition of tasks directly to the orchestrator preserves human cognitive energy. The user reserves their focus strictly for high-level project judgment and final visual approvals. The final hurdle is that AI agents simply aren't entirely self-sufficient yet. Complex, cross-disciplinary campaigns still require direct human intervention to bridge the gaps in the AI's logic. To solve this, the orchestrator introduces shared workspaces. This visualization shows two human specialists, a product designer and an engineer, operating on a single digital canvas. Each human commands their own distinct cluster of AIs. This layout creates a seamless handoff process. The designer can finalize a visual concept, and the resulting specifications are passed directly across the canvas into the engineer's coding agents, immediately initiating the build phase. The system also maintains a continuous chat log for soft collaboration. Agents automatically broadcast notifications about which files they are modifying, keeping human users and other AI swarms aligned on the project state. True multi-agent orchestration involves building a transparent, lateral ecosystem. It allows both human directors and AI nodes to continuously adapt and respond to each other's actions in real time. The speed of software engineering is no longer dictated by how fast a single person can type out a string of code. Scaling our daily output relies entirely on adopting spatial user interfaces, granting secure autonomy to isolated containers, and leaning heavily into lateral collaboration. The individual contributor is stepping back. The optimal human role is now positioned at the center of the workflow, acting as the conductor of a massive AI symphony. Orchestrators like AgentCraft are highly experimental right now, but they prove exactly where the industry is heading and what the daily interface of a developer will soon look like. If you want to dive deeper into building these AI agents and try out hands-on coding, check out the Learn by Doing with Steven YouTube channel and explore his tutorials across all platforms. And for high-level discussions detailing data and AI strategy, listen to the Steven Data Talk podcast. It is available right now on YouTube Music, Spotify, or wherever you get your podcasts. Links are in the description. Engaging with these orchestration paradigms now is a practical step toward commanding tomorrow's automated workflows, rather than being overtaken by the speed of their execution. A 1 trillion parameter language model requires massive amounts of memory. An NVIDIA B200 GPU, one of the most powerful chips available, holds 192 gigabytes of high bandwidth memory. As the model scales, it rapidly spills over the physical limits of a single chip. You could string thousands of these chips together, but connecting them introduces a severe physical limitation: data traffic. The cables linking these processors quickly become a high-speed traffic jam. Inside a single GPU, mathematical operations happen almost instantaneously using L1 cache and shared memory. But the moment a processor needs a piece of data stored on a completely different chip, that request has to travel across physical wires. The calculation speed plunges to a crawl while the system waits for the delivery. Training modern artificial intelligence requires orchestrating millions of calculations so precisely that the hardware never sits idle. At this scale, the primary challenge shifts from refining code to managing the physical movement of data across miles of cabling. This diagram shows the base unit of a computing swarm, called a node. This is a single server chassis containing 8 individual GPUs. They are bonded together by NVLink cables and an NV switch, allowing them to share data at speeds up to 1.8 terabytes per second. To scale up further, engineers group these nodes into larger pods, but they can no longer use those ultra-fast NVLinks. Instead, the nodes are bridged together using standard InfiniBand cables. The wider the physical network grows, the slower the connection speeds become. In a traditional network setup, passing a message between these nodes requires the CPU to manage the transfer. A GPU in one chassis must ask the CPU to copy the data, build a network packet, and ship it over, introducing significant latency. Modern clusters solve this using Remote Direct Memory Access, or RDMA. With RDMA, one GPU reaches directly across the InfiniBand cables and writes data straight into another GPU's memory bank. The CPU is left entirely out of the equation. High-speed cables and direct memory access provide the physical infrastructure. But coordinating the complex math required for language models across thousands of chips requires a highly specific software vocabulary. Engineers orchestrate this math using collective operations. Instead of manually programming how one specific chip talks to another, these operations provide simple, universal templates for how the entire swarm moves data. If a large matrix of data needs processing, it can be broken into equal pieces and scattered across multiple chips. When the local work is done, those separate pieces are gathered back together into a single, complete dataset. To find a global result, the chips must consolidate their individual findings. In a reduce operation, each chip submits its local calculation to a central point, where the values emerged into a single sum. The most vital operation for AI training is the all-reduce. It calculates that final sum and instantly mirrors that exact answer across every single chip in the system. A model trained on 1,000 chips requires millions of synchronized updates. Executing these precise scatter, gather, and reduce commands ensures the GPUs spend their time calculating math rather than waiting for data to arrive. This diagram illustrates data parallelism. Every single GPU holds a complete, identical copy of the entire neural network. The training data itself is cut into slices, and each chip learns from its own unique slice. After every round, an all-reduce operation averages their findings, keeping all the models perfectly synced. When the model itself is too large to fit on one chip, engineers use tensor parallelism. Here, the individual layers of the network are literally sliced apart. One GPU processes the left side of a mathematical matrix, while another chip handles the right. Because the math in one half of the layer constantly depends on the other half, the chips must rapidly swap huge volumes of data. This creates so much communication overhead that tensor parallelism is strictly confined to chips physically sharing a high-speed NVLink connection. The third strategy is pipeline parallelism. Rather than slicing layers in half, the network is split by depth. One GPU runs the first 10 layers of the model, processes the input, and then hands the result off to the next GPU, which computes the next 10 layers. This assembly line structure creates idle time, known as pipeline bubbles, where other chips sit waiting for their turn. To fix this, the training data is chopped into tiny fragments called microbatches. The first chip processes and pushes one microbatch forward, immediately starting the next one, maintaining a constant flow of data down the line. An engineer's choice between data, tensor, or pipeline splitting is dictated entirely by the physical architecture of the data center. The length of the cables and the speed of the switches decide exactly how the math must be routed. In modern massive AI labs, no single strategy is used in isolation. Engineers weave all three methods together into a system called 3D parallelism. They execute tensor parallelism across the 8 tightly linked GPUs inside a single rack. They scale out using data parallelism across thousands of nearby nodes in the pod. Finally, they bridge the slow connections between entirely separate buildings by layering on pipeline parallelism. Algorithmic brilliance creates the model, but physical throughput determines if it can actually be trained. The AI revolution relies on this precise coordination between silicon hardware and the software that dictates its traffic. Understanding the theory of distributed systems is only the first step. To completely grasp these concepts, you need to write the collective operations and test them on actual hardware. You can start practicing these network architectures on the Learn by Doing with Steven YouTube channel. And for more deep dives into the engineering behind artificial intelligence, check out the Steven Data Talk podcast. We interact with AI through a simple text box, but that interface is a leaky abstraction. When you rely solely on prompting, you restrict yourself to a predefined sliver of the actual design space, completely walled off from the mechanics driving the output. To understand how these systems actually operate, you have to bypass the API entirely. You must tear up the entire software and hardware stack and examine the physical limits of the infrastructure. One way to frame the challenge of training is as a product of efficiency and resources. If accuracy is the objective, researchers must treat algorithmic efficiency as the primary lever for maximizing the output of a fixed compute budget. At the frontier scale, where training runs cost hundreds of millions of dollars, You cannot achieve higher accuracy by simply throwing more hardware at the problem. You have to ruthlessly optimize the algorithmic design to squeeze every possible operation out of your memory bandwidth. Constructing a language model from the ground up requires mastering 5 specific engineering disciplines. But before any parameters are updated or matrices are multiplied, the entire process relies on a bedrock layer of data compression. Understanding these layers step by step is the necessary path to transition from querying a pre-existing system to architecting a new one. The foundation is training basics. This is where we define the mathematical shape of the system, selecting the transformer architecture, allocating parameters into a mixture of experts, and tuning hyperparameters to maintain strict stability. The second layer is systems. Processing chips are extremely fast, but they sit physically separated from where the data is actually stored. Moving information from memory into the processor creates an intense structural bottleneck. To close that gap, engineers write custom CUDA kernels. These are specialized software instructions designed to minimize data travel, locking the compute sequences to match the exact high-bandwidth memory transfer speeds. Above that sits the third pillar, scaling laws. When a single training run carries an enormous financial cost, trial and error is no longer an option. You extrapolate performance using strict mathematical curves established on smaller models, predicting the exact loss you will achieve before the full-scale run even begins. The final 2 tiers dictate the model's actual utility: data curation and alignment. Here, vast reserves of raw web crawls are aggressively filtered and deduplicated before applying weak supervision techniques like direct preference optimization to shape the model's ultimate output behavior. To make this entire stack operate, we have to look back at the precise moment raw text first enters the machine. While alignment and scaling generate the majority of public interest, the throughput of the entire stack is capped by how effectively we compress raw text into the machine. A neural network has no concept of a human alphabet. The transformer architecture operates strictly on numerical indices. The most obvious way to translate text is to assign a unique integer to every single character. But treating every letter as its own data point stretches sentences into highly elongated, inefficient sequences. This directly triggers the core constraint of the transformer architecture. The computational cost of the attention mechanism scales quadratically relative to the sequence length. If you feed a character-by-character sequence into the model, that squared cost curve spikes. It instantly exhausts the GPU's memory bandwidth, grinding the entire training process to a halt. You could try the exact opposite approach. You could map entire, complete words as individual indices, keeping the sequence lengths as short as possible.
But natural language contains millions of rare words, misspellings, and names. Attempting to map them all creates an unbounded, massively expanding vocabulary. This introduces severe matrix sparsity, transferring the overload directly to the embedding layer and blowing up the memory footprint in a different way. Rigid rules create a trap. Small units exceed compute limits, large units exceed memory limits. To thread the needle, the system requires an adaptive, dynamic compression algorithm. The industry standard solution is an algorithm called byte pair encoding. The process begins by stripping all text down to raw UTF-8 bytes. Because a byte can only hold 256 possible values, the system starts with an absolute baseline vocabulary size of exactly 256. The algorithm then sweeps across the entire training corpus, searching for the single most frequently occurring adjacent pair of bytes. When it finds a dominant pair, it merges them into a brand new token index and appends that new integer to the master vocabulary list. By replacing every instance of that pair across the entire dataset with the new single integer, the algorithm mechanically reduces the data volume, explicitly shrinking the total sequence length. This is a strictly iterative loop. The software scans the data again to find the next most frequent pair, and it is now fully capable of targeting the newly minted tokens. If our new token represents the letters T and H, it might quickly identify that this index sits right next to the byte for the letter E. It merges them, creating token number 257 to mathematically represent the complete word the.
Through thousands of repetitions, the algorithm reaches an equilibrium. Highly common linguistic concepts organically fuse into single, hyper-efficient tokens. Conversely, rare words and strange misspellings aren't discarded or flagged as errors. They simply remain subdivided into their smaller, constituent byte chunks, completely preventing the system from ever encountering an unknown sequence. This mechanism directly satisfies the requirement of our starting efficiency equation. It maximizes the data compression ratio for every document passing through the system. BPE functions as a computational safeguard. It manages the quadratic expansion of attention costs by ensuring the transformer operates on the most information-dense sequence possible. Tokenization proves that securing algorithmic efficiency must start before the first piece of data is even processed. By adaptively compressing bytes into optimal sequences, the algorithm perfects the geometric shape of the inputs long before the first neural matrix multiplication takes place. This philosophy of optimization persists as you move up the stack. From writing custom logic for memory transfer, projecting performance through predictive mathematical curves, to aggressively sanitizing raw internet scrapes, every layer of the architecture is an exercise in resource extraction. The seamless interface of a chat window hides a physical reality defined by the orchestration of thousands of interconnected GPUs and petascale data streams. To push the boundaries of what these systems can achieve, you have to break past that clean API abstraction and confront the physical and algorithmic limits governing the hardware. Pushing the frontier of intelligence requires more than prompting. It requires an engineering mindset that confronts the physical and algorithmic limits of the hardware itself. To continue exploring applied model engineering and hands-on systems architecture, subscribe to the Learn by Doing with Steven YouTube channel. And for deeper dives into AI architectural strategy, listen to the Steven Data Talk podcast, available now on YouTube Music, Spotify, and Apple Podcasts.
When we talk about artificial intelligence, we usually picture clean neural network architectures and pure mathematical equations. The reality of creating these models is bound by physical space and harsh electrical constraints. Training a large language model requires warehouse-scale physical infrastructure. You are managing thousands of physical components, orchestrating the flow of electricity, heat, and data across massive server racks. Within those racks, engineers face a severe bottleneck. Look closely at the spec sheet for a modern H100 GPU. It promises nearly 1,000 teraflops of raw computing power. Yet, even when top laboratories actually train models on this hardware, they rarely achieve more than a 50% utilization rate. Half the hardware's capability sits idle. Training a large language model is a deterministic systems engineering problem, dictated by strict physical limits. To understand those limits, we have to start at the absolute bottom. Every parameter, gradient, and activation in a network is stored in memory as a tensor. Traditionally, the standard format for these numbers was float32. This format provides high resolution, but it demands 4 bytes of memory for every single parameter. For models with billions of parameters, that footprint immediately exceeds available memory capacity. Cutting the bits in half to float16 shrinks the exponent bits so much that the format loses its dynamic range. If you try training a deep network with it, numbers that get too small turn into zeros, and numbers that get too large cause overflow errors, crashing the training run. This diagram shows how the industry solved the problem with a format called bfloat16. Instead of equally shrinking the number, it sacrifices the mantissa, the fraction part responsible for high resolution. It shifts those bits over to maintain the exact same exponent size as float32. You lose decimal precision, but you maintain the necessary dynamic range to prevent the model from overflowing. Hardware engineers are currently pushing even further into 8-bit and 4-bit precision. Because 4 bits cannot cover the necessary dynamic range natively, they work around the physical limits by grouping values into blocks and applying a shared scaling factor to the entire block. Selecting this bit-level precision establishes the absolute physical floor of the entire model's memory footprint, long before a single computation is executed. Once the precision is set, those tensors must be moved and manipulated. In standard frameworks like PyTorch, developers manipulate matrices using arbitrary index-based transposes, requiring them to guess whether dimension -1 or -2 is the correct one to swap.
Systems engineers avoid this ambiguity by relying on a library called INOPS as a structural solution for managing complex tensor operations. INOPS requires you to use named dimensions. You declare exactly what you are doing, mapping a sequence and a hidden dimension directly to a designated output matrix. Any dimension not explicitly mentioned gets summed out automatically. This naming convention forces the developer's intent to perfectly map to the hardware's physical memory layout. Clean, unambiguous operational syntax allows us to calculate the deterministic cost of our compute. We measure this cost in flops. A flop with a lowercase s is a single floating point operation, a measure of the total math required. Flops with an uppercase s denotes floating point operations per second, measuring hardware speed. This animation shows the arithmetic cost of a forward pass through a basic linear layer. We take our input data points, dimension n, and we multiply them by our parameter matrix, dimension d.
Because each coordinate intersection requires one multiplication and one addition, the cost of this forward pass is 2 times the number of tokens, n, times the number of parameters, d. The backward pass requires twice as much work. The chain rule demands 2 distinct sets of gradients, one gradient with respect to the parameters and another gradient with respect to the inputs. That makes the backward pass cost 4 ND. 2 ND forward plus 4 ND backward yields the baseline calculation for language model training compute, 6 ND. Every single token passing through a parameter exacts a non-negotiable computational toll on the system. The chips have high bandwidth memory, where the tensors are stored, and specialized cores where the math actually happens. To compute anything, a massive stream of digital data must physically travel from memory across a narrow pathway into the accelerator. This introduces arithmetic intensity, the ratio of flops executed per byte of data transferred across that memory bottleneck. Consider an element-wise operation, like a ReLU activation. The system pulls a massive vector into the core, performs a single comparison to 0 on each number, and sends it right back. The ratio of actual math to data movement is incredibly poor. Contrast that with a large matrix multiplication. You send an n-squared amount of data across the wire, but you compute an n-cubed number of operations once they arrive. The arithmetic intensity scales positively as the matrix grows. This graph shows the hardware's physical limits, known as a roofline plot. The y-axis tracks achieved performance, and the x-axis tracks arithmetic intensity. The sloped line is the memory bandwidth ceiling, and the flat line at the top is the peak compute ceiling. Operations like a ReLU activation are trapped here on the sloped line. They are strictly memory-bound. The accelerator sits idle, waiting for data to arrive. A massive matrix multiplication pushes past the inflection point and hits the flat ceiling. It saturates the hardware and becomes compute-bound. Model flops utilization hovers at 50% because the hardware is constantly starved for data transfer, not compute capabilities. Let's open the ledger and calculate the true memory cost of a single parameter during training. Using bfloat16, the baseline weight takes 2 bytes. The resulting gradient requires another 2 bytes. To navigate the loss landscape effectively, the Atom optimizer must constantly track the first and second moments of the gradients for every single weight. Accumulating these running averages in low precision causes severe mathematical instability. Atom requires standard float 32, instantly adding a massive 8-byte footprint per parameter. The model weights are a fraction of the total cost. The optimizer states are what actually drown the GPU's memory. To stay compute-bound and maintain high arithmetic intensity, we need massive matrices and large batch sizes. But processing those large batches blows up the high-bandwidth memory with massive activations and optimizer states. To prevent the system from crashing, engineers implement 2 critical pressure valves. The first is gradient accumulation. Instead of processing a massive batch at once, the system slices data into micro-batches. It runs forward and backward passes on these smaller chunks to save memory, adds the results into a holding pool, and only steps the optimizer once the full batch accumulates. The second pressure valve is activation checkpointing. Normally, the forward pass saves every layer's activation for calculating gradients. Checkpointing intentionally drops most intermediate activations, flushing them to keep memory empty. During the backward pass, the system simply recomputes missing activations from the nearest saved checkpoint.
Training a large language model at scale requires engineers to juggle bytes, cheating physical memory walls while fighting to keep arithmetic intensity high. If you want to take these theoretical frameworks and apply them practically, I highly invite you to check out the Learn by Doing with Steven YouTube channel and other platforms. And for deeper discussions on the data engineering that fuels all this, tune in to the Steven Data Talk podcast, available on YouTube Music, Spotify, and various other platforms. Links are in the description. Look at a modern GPU. It is an incredible piece of engineering, but it is bound by a hard physical limit, its onboard memory capacity. This chart shows exactly what it takes to store a large language model. To train a 100 billion parameter model, we need space for the weights. We need memory for the gradients. We need massive allocations for the optimizer states, tracking the first and second moments for algorithms like Atom. And we need space for the transient activations generated during training. Add those up, and the required memory footprint violently shatters the capacity limit of any single piece of silicon on the market. Because of this, the individual GPU has been replaced by the entire multi-rack data center as the base unit of compute. Stringing thousands of machines together introduces two distinct engineering bottlenecks. Compute scaling involves keeping every chip constantly fed with math, while memory scaling requires sharding the model parameters across the network without losing the overall mathematical state. Model scaling is now a distributed systems problem, defined by the hard trade-off between sharding memory and minimizing the time spent moving data across a cable. Let's examine the standard approach to this problem, naive data parallelism. Here in this interface, we split the training data batch across multiple GPUs. Each chip calculates gradients for its own slice of data, and then they all synchronize. But data parallelism hits a memory wall. Every single chip holds an exact, fully replicated copy of the model parameters, the gradients, and the high-precision optimizer states. This redundancy wastes massive amounts of capacity. To fix this, Stage 1 and Stage 2 of the Zero algorithm shard the optimizer states and the gradients. Each GPU only holds a fraction of that data, only exchanging it over the network when it is needed to process an update. The final step, known as fully sharded data parallelism, or FSDP, shards the model parameters themselves. By fracturing the weights across the entire cluster, the per-GPU memory usage drops severely. To make this viable, engineers have to overlap network communication with mathematical computation. Notice how the parameters for layer n+1 are being gathered over the network at the exact same moment the GPU is calculating the matrix multiplication for layer n. This overlap effectively hides the physical latency of the network behind the time it takes the silicon to finish its matrix multiplications. While FSDP clears the parameter memory wall, it aggressively consumes the global batch size. If we run out of data to split, we hit a new scaling limit. If the global batch size drops too low relative to the GPU count, the math finishes before the next set of parameters can arrive. The system becomes purely communication-bound, leaving the chips idle. To keep the chips busy at low batch sizes, we use pipeline parallelism. We take the sequential layers of the neural network and physically separate them across different hardware nodes along the depth axis. This creates a synchronization gap called the bubble. Because the layers are sequential, the GPU holding layer 10 has to sit idle, waiting for the GPUs holding layers 1 through 9 to finish their work and pass the data forward. To shrink this bubble, the data is sliced into smaller microbatches. As soon as a GPU finishes one microbatch, it hands it off and immediately starts processing the next one, compressing the idle time in the schedule. Advanced setups use zero-bubble pipelining. By separating the urgent backpropagation of derivatives from the less urgent weight gradient calculations, engineers can slot the weight math into the remaining gaps, filling the pipeline completely. Pipelining is highly efficient for slow network connections between racks because it relies purely on point-to-point communication, passing only the activations forward. But depth splitting still fails to address the final memory hurdle, the enormous activation humps generated during training. At large sequence lengths, the memory required to store transient activations completely dwarfs the space needed for the model's parameters. To reduce this, we use tensor parallelism to split the model along its width. Instead of dividing the layers, we slice a single matrix multiplication into smaller submatrices, compute them simultaneously across different chips, and then synchronize the partial sums. Tensor parallelism requires massive all-to-all synchronizations for every matrix multiplication. It is incredibly bandwidth-hungry, forcing it exclusively onto ultra-fast interconnects inside a single server chassis. Even with the matrices split, artifacts like layer norms remain. Sequence parallelism shards these specific remaining elements across the sequence dimension, materializing them only when the math requires it. Width splitting effectively neutralizes the activation memory threat, but its appetite for bandwidth dictates exactly where it can physically sit in a server rack. For architectures like Mixture of Experts, we shard the routing mechanisms and individual experts across devices using expert parallelism. For these models, expert parallelism is preferred over matrix slicing. It is more efficient to route sparse tokens to specific chips than to synchronize dense tensors. And when the context window exceeds hardware limits, context parallelism passes activations in a continuous ring to distribute the sequence across the entire cluster. The efficiency of these strategies, specifically how much tensor parallelism we can use, depends entirely on the physical layout of the network. Google's TPU architecture uses a toroidal mesh topology, where every chip connects directly to its neighbors in a wrapping 3D grid. This differs from traditional GPU clusters, which rely on a hierarchical fat tree topology. Communication is fast at the bottom, but as data moves through the pods, the spine switches create bandwidth choke points that restrict how we can shard the math. Because toroidal meshes offer uniform neighbor bandwidth, they permit larger tensor parallel clusters than fat trees. The physical wire geometry dictates the mathematical algorithms we deploy. These techniques form the 4D configuration rule for frontier models like Llama 3. 1. Assign tensor and expert parallelism to highest bandwidth internal links. 2. Deploy pipeline parallelism, or FSDP, across slower switches until parameters fit. 3. Use data parallelism on remaining GPUs to maximize throughput. These systems require constant oversight and hardware redundancy. During the Llama 3 run, hardware failures forced the team to recover the system 148 separate times. At this scale, the success of a model is determined by the precision of the network scheduling and the stability of the distributed system. To dive deeper into the technical architecture of modern AI systems, check out Learn by Doing with Stephen on YouTube and the Stephen Data Talk podcast on Spotify and YouTube Music.